All right.
All right, cool. All right, welcome, guys. My name's Simon, and I'm here with Newman as well. We're just going to talk to you guys about the intro to the shenanigans and spiderweb that is the World Wide Web. Real quick, it's the exact same slide that I used in the networking presentation. My handle's One Nut Wonder. I'm pretty involved with the club, ISTS, Red Team. One of my favorite areas in security is web, but we've gone over this before, so we'll just go to Newman's.
This is also, I just copied and pasted my slide from my last presentation. I'm Newman. Uh, I'm interested in cryptography, but today we're talking about web. So when we say the web, I mean, there's lots of stuff on the internet, right? Web servers, file shares, remote access stuff. But when we're talking about the web, we specifically mean the World Wide Web, websites, web pages, things like that. Like when you go into your browser and go to a website, that's specifically what we're talking about here. There's tons of other stuff that happens on the internet, but we're just talking about when we talk about the web, that's the subset of internet traffic we're talking about. Just to be clear.
All right, so before we get too deep into the weeds here about this stuff, let's go over some just high-level vocabulary that you're going to hear throughout this talk. The first is HTTP. That's going to stand for your Hypertext Transfer Protocol. And that's just essentially the web protocol. That's what's used for the clients and servers to communicate. That's what your browser is going to communicate with the server whenever you want to pull up those dang spicy memes. It's going to send out an HTTP request, and the server is going to send a response. That's the core of web, is this kind of back and forth request and response, and we'll see more of that later. And then generally, this content is served back to you in the form of HTML, CSS, and JavaScript. Those are like the three main content types that you'll actually be receiving back. Now, HTML is just like a markup language. It is not a programming language. It's a markup language. Very important. But this is just going to define how the page and how the content's structured. You can define certain tags, bold, italics, links, images, all of that fun stuff. We'll talk more about it later. And then you have the CSS, which stands for Cascading Style Sheets. Cascading Style Sheets. Oof, it's too early. But this is just going to make everything look pretty. It's a real pain in the butt to try and work with. There's tons of memes and jokes about it. Trying to center things, get it the right color, and get things to look the way you want. But this is just going to provide that beautiful looking website that we all know and love. And then we have everyone's favorite JavaScript. It's also known as ECMA script or ES, but this is just going to be like client-side code that is going to run in your browser to make the websites more interactive, more engaging. Some games are written in JavaScript. It just kind of makes the website more interactive. You can also do styling through frameworks in JavaScript such as Bootstrap, but that's a whole other thing. But these are just the three different types of content that the web server will be sending back and you'll actually be viewing through your web browser.
So let's just go over some of the basics of HTTP. And if anything here, if you feel like I'm going too fast, don't worry. This is just an overview. We're gonna go over all of this again in more detail in the slides after this. So first off, HTTP is an application layer protocol. That means it runs on top of TCP, at least usually. We'll talk about that in a second. HTTP, which is the plaintext version, uses port 80 on TCP. And HTTPS, which these days is the more common one, uses port 443. And HTTPS is really just HTTP wrapped in TLS for encryption. I mentioned it's usually TCP. There's the newest version of HTTP called HTTP3 uses UDP to be faster, but we're not going to really talk about that. It's different from HTTP older versions in a lot of ways, and it's not that widespread support, so don't worry about it too much. If y'all remember from the networking week, TCP is stateful. You create a session, there's sins and acts and resets and all that good stuff. And HTTP goes on top of TCP, and TCP is stateful, but HTTP itself is stateless. So what that means for us is that each request and response pair is completely independent of every other request and response. When you make an HTTP request, when you make the next request, the server isn't automatically going to know that you're the same person making the same request. So we have to do some workarounds to get some state in our web applications, like when you log on, but we're going to talk about that in a bit. You can have multiple different request types, and each request different type is distinguished by different methods. And these methods have a certain semantic meaning. You can, if you want to, use them for whatever you want, but each method has a certain use that it's generally used for. We'll talk about those. So you make a request of a certain method, and then you get a response. And each response has a certain status code. That's basically like a short description of what happened, what kind of response is it? Did everything work out fine? Do you have to go somewhere else? Did something mess up? That's described in the status code. At a minimum, a request needs three things: a method, a path, and a version. So the method could be something like get, saying what you want to do. The path is whatever resources you want to request. So maybe /index.html to get the home page of the website, usually. And then an HTTP version, because different versions can talk slightly differently to each other. So maybe you want to say HTTP/2. So that's the bare minimum you need for a request. You always need those three things. You can have more, but you need to have at least those. Both requests and responses can, but don't necessarily have to, have headers and a body. Your headers in an HTTP request or response contain metadata about it, like extra information about the request or response. The body of a request or response is like the actual payload. That's what, if in the case of a request, that's some data that you're sending to the server for processing. And in the case of a response, that's whatever resource you requested. So if you're going to, say, a website, that would be the HTML page that you're downloading in the response payload.
So Newman just mentioned kind of the broad overview of what an HTTP request and kind of what a response is going to look like. So now we're just going to go through and we're going to break down each one of those things individually. So first, we have the method. So this is one of those three things that you're required to have in your request in order for it to even work or be processed by any web server. So here is a list off of the Wikipedia page for HTTP methods. And so the first one, and by far the most common, is going to be a GET request. Okay, so this is just essentially you want to get a resource from the website, and then the server is going to fetch it and get it for you and return it to you. So anytime you type in like going to a website like www.google.com, you're more than likely your browser is going to send a GET request, and then Google's going to return the main Google homepage for you. And then we also have the head method. Now, the head method is essentially the same as a GET request, but there's going to be no body. So in a GET request, whenever you get the content back, the content is given in the body of the response. The head, you can just think of it as getting the headers. All you receive back from the server are just the HTTP headers from the response. So the head method is really useful for just getting quick information about a web server, maybe like what it's running, some backend information, cookie information, just kind of the headers that it's going to be sending back and or expecting from you. And it's much faster because there's way less data being transferred back and forth because you don't have to load all of the web page information that the server may or may not send back if you had just sent a GET request. Next, we have some like data changing or data manipulation methods, which are post, put, and delete. So post and put are going to generally be used for uploading data, such as like if you do a file upload, it's generally used via post or put. Form submissions, like login form submissions, are generally and should be post methods. As with most things in web, you can do a lot of things with like however you want. For example, you can do form submissions via GET requests. You can put them in URLs. So if you've ever seen a URL where it says like user equals and then your username, that means they're sending that data via a GET request instead of a post request. Now the post and put requests will generally have that information contained in the body of your request rather than in the parameters. So it's a little more hidden, a little bit harder to see. And then delete is used for deleting a resource. So you actually specify a resource to the server. And then if the server, accepts it, it'll actually delete a resource. So it's very obvious that it's not a good security measure to have the delete method allowed on your web application. But, you do you. I'm not going to stop you if you want to use it. Next, we have the connect method. Now, important distinction here is that the connect method is different from the connection header. Later on, we'll talk about headers, and there's actually a connect. It's either connect or connection. I don't remember the semantic, like which spelling it is, but there's a header where you specify the connection as well. But this method will actually open up a tunnel, open up a connection, and I believe it's generally used for like proxying in a server. You can open up a tunnel with it. I personally haven't seen it that often, but I have seen it like once or twice used. The next method that's actually pretty important for you to know is the options method. Now, what this is going to do is you'll send a request to the web server, and if it supports the options method, which most of them do, if it supports it, the web server will return the methods it supports. So one of the headers it will return will be an allow header, and then there will be a list of HTTP methods that web server supports. So if you're unsure what that web server is accepting right there, you can send an options method and it'll respond with like I support get, head, and post. Like those are the three that I'm going to accept and actually process with my application that I'm hosting. So options is super useful for reconnaissance and debugging, as well as just web app pen testing in general. Next, we have trace. Personally, I've never seen this like used in the wild, and I've never used it, but it's supposed to act similarly to traceroute. So if you know anything about traceroute, you can use it to hack your ISP and just get all that free internet. So this will allow you to hack any website if you know how to use it properly. But essentially, it just gives you back a trace of the path that your request took. Again, similar with traceroute and ICMP and things of that nature. And then the final method that we're going to talk about is just patch. Personally, I've never seen this. I'm going to hand it off to Newman here in a quick second because he has actually used this before. But patch is similar to put and delete, where you can specify a list of changes to the content or the resource to make. And then the server will actually update them based on that list of stuff you give them. So Newman, if you want to talk about this one a little more, that'd be great.
Yeah, so post is of the ones that I'm going to talk about. Post is the ones that you only usually see when browsing normally, but post, put, delete, and patch are mostly used in APIs. So when you're programmatically interacting with the web server to do, usually really just basically interacting with the database to create and delete resources and modify them. So post is generally used to create a new resource. Like say if the thing that we're creating is tweets, post could be used to just create a new tweet. You give it the content, you say, here's my tweet content, create this new tweet for me. The put method is a little bit different. With put, you have to specify the unique identifier of whatever the resource is that you're going to create. So put can be used to create a resource. If I wanted to put a tweet, I would have to generate my own unique ID and give that to Twitter along with the tweet and say, create this at this identifier. Delete is, I mean, obviously, you're not going to delete a web page with a delete request, but if you're in an API and you authenticate properly, you can use delete to delete a resource. Like maybe you want to delete your tweet if you made some kind of typo or something. And then patch is similar to put, but there's a little bit of a distinction. With put, every time you make a put request, it completely overwrites whatever is there. So if you have some extra information, like let's say in my tweet, I have an image that I'm also posting. So every time I make a put request to write that tweet, I have to have the tweet content and the image. But if I only want to modify the tweet like text content, then that's kind of wasteful because I'm sending the image up every time with it as well. But with patch, you can do the same thing as put. You can modify a resource by its ID, but you don't have to provide everything. You can just give to the server the things that you want to modify, and it'll only update those things in place. Whereas with put, if you didn't include those other things, they get erased. So for example, if I just wanted to change my tweet content and not the picture, I could do a patch request with just the new tweet content and the picture would stay up there. So it's a small difference, but you usually see it in the context of APIs and things like that.
Cool. Thanks.
Yeah. So we talked about methods, which are kind of like explaining what kind of request you're sending. Status codes kind of explain what kind of response you're getting back. So there's tons of different status codes, and each one's just a 3-digit number. They're generally grouped into 5 types. The 100s are informational. That means that they're not used that often, but it usually means here's a little bit more information. Now wait for the real response. It'll come later. The 200s just are general success methods. Each one has a slightly different meaning, but usually they mean whatever you asked the server to do was successful. The 300s are redirection, which mean your client would have to handle that response and go send your request again somewhere else. This is commonly used, say, if you go to a website over HTTP, redirects can be used to send you over to the HTTPS, the encrypted version. That's a really common usage. 400 status codes mean there's a client response. So the person or program sending the request messed up with their request in some way. Maybe it's the wrong format or they're not authorized or something like that. And then you have 500 errors, which are server-side errors. Usually you can't really do anything about those. It's just to let you know, hey, something's going wrong, try again later maybe. And then this http://statuses.com link, that's a good website you can go to check out all the various status codes and what they usually mean. There's a standard set of status codes, and then some websites and APIs add their own custom ones that aren't really standardized. So yeah, again, like what specifically status codes you're looking for and what they mean. They're generally agreed upon, but you can really nobody's enforcing that you use a specific status code. So different APIs can kind of do whatever the heck they want with their status codes. I've seen some websites that will return a 200 code when the server has crashed, and then in the body somewhere say, oh yeah, by the way, this is a server error. So welcome to the wild west of the web. People do whatever they want.
Yeah, and another important thing to mention real quick about the 500 server errors, if you're browsing the internet normally and you're on a website and you're not trying to do anything malicious, you're trying to use it as it's intended, the 500, there's probably nothing you can do about. However, if you're specifically doing a web application test, like you're actually testing the application and its security, and say you put in some input into a form and then you submit it and you get a 500, that's kind of a good thing for you, because that means you got some bad input into the server and made it, break. Like the application didn't know how to handle your input. So sometimes they can be a good thing and they are your fault. So just keep in mind like what you're using it for. So now let's talk about the HTTP headers. So now we're moving slowly down into the request body a little bit, or not the body, but we're getting to the body. So the headers are different from the method, and the headers are really just the metadata of the request. If you look at an HTTP request, especially from like RIT, there can be like 10 to 20 different headers in the request. Like some web servers just go absolutely nuts with it, and some developers go nuts with it as well. But this can contain anything from the type of web server running. So for example, Nginx will sometimes send its own header with any response it sends. It'll say like Nginx / like its version number. That's obviously super useful because now you know the Nginx version. You can go look for CVEs or other vulnerabilities that Nginx has in it. All of these headers, you'll notice, will follow a key value pair syntax. You'll have the header followed by a colon, then a space, and then the actual like value for it. And these can be, again, anything you want them to be. There are ones defined by RFCs and ones that are generally agreed upon. But again, you'll notice as you dig into the web, developers and just anyone will do anything they can to either A, fix the application in a way that's good for their business, or two, they just may not be aware of an RFC rule and they just won't implement it that way. So you'll see a lot of different headers that you may have never seen before, and that's because they may be custom. Generally, in a custom header, they'll start with an X. However, be careful with this because the RFC has slightly changed over the years to actually standardize some headers to start with an X. I believe an example of that would be X forwarded from. I think that's an RFC standard header that starts with an X. For example, in HackerOne, it's a bug bounty program. Some companies will ask you to put in a header that says X-HackerOne, and then as the value, your username. So that way in their logs, if you break something, they know that you weren't actually being malicious. You're a security researcher. But basically the headers are just going to give you the metadata, and it can tell you anything from the content it's expecting, how long the body is, whether or not the response is cached, and even more importantly, the user agent. So whenever you request a website on your desktop versus your phone, that's generally how like the reactive the UI designs will change. So like on your phone, you obviously get the mobile version. On the desktop, you get the desktop version. And sometimes that's done through the user agent because your phone will send like an Android user agent, whereas your desktop will send just like the Firefox user agent or something of that nature. So that can help tell the web server, what's up.
So cookies are contained in a special HTTP header, the cookie header. Go figure. And earlier I was saying that HTTP isn't stateful. Well, cookies is how we work around that and get some kind of state within a web app. So, for example, when you log in, this is how the web server knows that you're still the same person after you log in, and not some other random person. Cookies are automatically passed back and forth between the client and the server. The server will tell the client to set a cookie, and then every time the client makes another request to the server, it'll automatically pass all of the cookies that it's stored for that server with every request. So it can be used for a number of things like advertisement tracking, but cookies are generally used to authenticate a client and identify which client it is to the web server. So they're stored in a client, usually in something called a cookie jar. It's so cute, I know, cookie jars. But they're set by the server with the set cookie header in a response. So if, say, you log into the web server, when it sends the response back saying, "Okay, you're all good, you're logged in," that response will include the set cookie header, and then it'll include usually it's named session ID or something. It kind of depends on the back end, but some identifier that identifies you to the server. When you log in, it'll make sure you're authenticated and then record in its session database somewhere that this session ID is associated with this account. And it'll save that, and then it'll send you that session ID in the set cookie header. And then your client will save that and send that session ID back in every request in the cookie header. And then when the server sees that session ID cookie with that specific value, it'll look it up in its database and see, oh, hey, this session ID is associated with Newman's account or Simon's account, and then it'll have you authenticated with that account. In some cases, these are just randomly generated values that are stored in a database somewhere. So it's not as important to have some kind of tamper protection because, I mean, if you change your session ID, it's kind of like guessing a password or a key. It's random. But some servers and backends will implement session IDs and identifiers a little bit differently. Like, for example, JWTs or JSON Web Tokens. These sorts of tokens will embed your authorization information in the token itself. So it might say, instead of just having a random value that's stored in a database somewhere, the token itself might say, this token authorizes whoever holds it under Newman's account as an administrator user, or maybe as a normal user, like basically the identity and what permissions they have. And all that's just stored in the token. So you want to make sure that somebody can't tamper with this and just change their user authorization to admin, or change their username from like Newman to super user or something like that. So some servers that use cookies like that, like JSON Web Tokens, they'll implement some sort of tamper protection. Maybe the cookie is encrypted with a shared key with all the web servers. Maybe the web server signed the cookie and stored that signature within the cookie. But it depends. You'll have to check with your, you'll have to look at the web app and see what it's doing. But that can be one area that is interesting to look into, depending on what kind of identifier cookies you're getting. Because if the server is using some kind of weak cryptography to implement some tamper protection on their cookies, you could break that and maybe modify your cookies to get more access than you should have. So like we're saying, cookies used a lot for authentication and identification. So if you're able to steal someone's cookies from their browser, then you're able to impersonate them entirely. Usually, or sometimes there's other methods of identifying somebody with the cookie, but usually if you get a cookie, that's basically the keys of the castle. You can totally impersonate them on the website now.
Okay, so we've made our way basically through the entire HTTP request and response syntax and what it's going to look like, and the last part of that is the HTTP body. So this is an optional part of the request and response. They're not required. As we mentioned before, the head method, for example, the response and request of that does not contain a body at all. So the body is just going to be, it's going to contain anything that you send to the server for a request. So for example, in a post request, say you're logging in, the body of a post request will contain your username and password fields, those values in there, and they will be posted to the server via that post request. And then in the response of a server, for example, in a GET request or in a GET response from the server, the body of that response will contain the web page. So it's going to contain all the HTML, all the JavaScript, the CSS. Well, the CSS may be fetched from an external source, but that's a different thing. And it'll also contain anything that the backend languages like PHP have added into the code before returning it to you. So just think of the body as like the content you're receiving or sending. So if you're uploading a file, the body will be the file information, and et cetera, and stuff like that. It's a pretty simple part of the HTTP request and response, but the overall format of it is really going to depend on the API or the backend or whatever language you're interfacing with. They may do things slightly differently, but for the most part, an HTTP body is pretty straightforward. It's not like headers where like you can just make up garbage and then it's, you know, it does whatever you want. The body's just the content, so it's pretty straightforward.
So we've been talking a lot about what requests are and what they look like, but how do you actually make a request? Well, first, your browser is the most common way of making requests, and we'll talk about dev tools in a bit, but that's actually a decently powerful way of making requests graphically. But there's other ways you can make requests outside of the browser. You can do it programmatically with different. Most programming languages will have some sort of HTTP library, like with Python, there's requests, which is a really powerful one. With Golang in the standard library, they have net HTTP. And Rust Well, pick your poison. There's tons of them, and any other language. Lots of languages have different HTTP libraries. I mean, heck, even JavaScript has HTTP libraries and is running in the browser itself. So if you're writing a program or an app or something, you're probably going to use a library. But if you're just running one-off commands or one-off requests, there's some command line tools you can use. And the most common one is probably going to be curl. Like if you're making requests in Bash or a shell, you're probably using curl. It's pretty nice. It's pretty easy to use. Sometimes you have to go and find the specific options and flags you have to use, but the documentation is pretty good. And it's very commonly used. So if you search up what you're trying to do with curl, you'll probably find a Stack Overflow page. It's also surprisingly powerful. The curl command is really just a command line front end to libcurl, which is this gigantic library for making requests and parsing responses, not only for HTTP, but a number of other protocols. It is a beast of a library, and it's written in C, and it's used by a bunch of other libraries. So if you're using a library like requests or something, it might actually be using libcurl in the background. But point is, if you're trying to do some stuff on the command line, curl is probably what you're going to use. Netcat, if you want to get fancy, you can use Netcat. That's another option. HTTP is still mostly a plain text protocol that's going to change in newer versions, but we don't really have to worry about that yet. So if you want to, you can theoretically connect to a web server with Netcat. Just type out your request and hit enter, and that can work. But it's kind of a pain. And it also only works for plain text. So if you have an HTTPS server, you can't use Netcat. But you could use OpenSSL, the command line for that, which has an SSL or TLS client embedded in it. So that command, OpenSSL as client connect, you'll basically be doing the same thing as Netcat, except it'll wrap that in TLS, and then you can type out your request. There's also some API design tools, either in the browser or like a desktop client, that you can use to build requests graphically that are a little bit more powerful if you want to be making requests repeatedly. There's lots of ways to do it.
Cool. So let's talk about everyone's favorite HTML and CSS. I know everyone here and everyone watching on stream strives to be a front-end developer, and everyone loves graphical design, and everyone loves building tables in CSS. I know I do. So let's just talk about those real quick. As I mentioned before, it's just how information is presented and formatted. HTML, it's a tag system. So you basically smack some text in, and if you want it to be bold, you enclose it in two bold tags, a beginning and an ending tag. The example right here on the slide is actually defining this text as body, and then H1 is header one. So it's actually going to be a big, big bold text, like a header, go figure. And then certain HTML tags can have attributes. So for example, we're creating a div here, which is basically just like a container, subcontainer type of thing. And you can give it an ID, and then using CSS, you can apply certain styles to things of that ID. So you can see in the CSS and div HTML example, we're applying the background color red to any div that has an ID of my div. So if we have multiple of those divs, all of them will basically inherit the background color red. It's pretty complex. I hate dealing with CSS. If I have to style anything on a website, CSEC 380, I just use Bootstrap, which is a JavaScript framework. Very, very copy and pasteable. Highly recommend. And the defaults on it look pretty nice. So that's what I recommend. But this is just kind of how HTML and CSS works.
JavaScript it was initially created just to make websites a little bit more interactive, so you're looking at more than just plain text, but it's kind of eaten the web. It's a scripting language that excuse me. It's a scripting language that runs in your browser. So each browser has a JavaScript engine that will interpret the JavaScript and then run it as whatever architecture, whatever bytecode it needs to. It's kind of like a Python interpreter in your browser, except it's JavaScript. It's inspired. It was when it was originally created. It was inspired by Scheme, which is the dialect of Lisp, which is a functional programming language. It's if you're familiar with Java, it's completely different from Java. That was a big thing when it was created, and still kind of is. It sounds like it's just a scripting language of Java. It's completely different. I think they named it JavaScript as like a marketing thing, but since it's a dialect of since it's inspired by Scheme, it's very functional, which is a certain style of programming language. So if you are familiar with more object-oriented things like Java or programming language like C, if you've never worked with a functional programming language, it can be really weird. And that's part of the reason why a lot of people hate it. Some people actually love it, but a lot of people in the security community, or at least at RITSEC, seem to not like it, just for whatever reason. It can also be run server-side, outside of the browser. Runtimes like Node.js and Deno are servers that will run your JavaScript on the server side, which is kind of nice because if you're a web developer and you've got people breathing down your neck to put out a web app quickly, if you can use JavaScript both on the browser and the server side, that can speed you up a lot quicker because you don't have to context switch as much. You're using the same language on both sides. And then you don't have to like figure out how to do things in two different languages. You can share code. So it has its pluses. It also has its downsides. It's designed to kind of interact with your web content, with your HTML and CSS. A common, very simple thing to use it for is form validation. So if somebody's typing in a form and you want to tell them as they're typing, if they're typing in the right stuff, that's a common way to do it. That's a common use of JavaScript. You could also use it for more advanced user tracking and even single page applications. So you go to a web page and you've got a whole application there in your browser. That's using a lot of JavaScript to do that. It can pretty much do whatever you want. It's a full programming language. Some people can use JavaScript to do bad things like steal your cookies and impersonate you. But it's pretty powerful. And then just wanted to cover this real quick because I was really confused when I started looking more into JavaScript to do some development. You might see JavaScript called ECMA script or ES. JavaScript is a standard that ends up getting implemented by browsers. So this standard is defined by ECMA, which is a standards organization like IEEE or something like that. So that's why it's called ECMA script. It's the script that they standardize. They publish a new edition every year. I think about 6 years ago now, ECMA script 5 came out. And then after that, they switched over to years. So ECMA script 2015, 2016, etc. You might also see it abbreviated as ES5, ES6, ES 2016. So if you see any of those, that's what it means. Don't be too confused or worried, like I was.
So you may be thinking like, wow, JavaScript sounds great. We can make our web pages interactive. We can tell the user they're screwing up in real time as they type things in. Well, JavaScript causes more problems than it helps, in my opinion, most of the time. JavaScript can be a very, very useful thing if you use it properly. However, you have to remember that JavaScript is client-side. Yes, there are those server-side solutions that Newman just mentioned, but the majority of the time, JavaScript will be running on the client's machine in their browser. What that means is that the client has full control over the JavaScript that you wrote and is running in their browser. So if you are relying on form validation with your JavaScript, like that is your only form of validation before it gets sent off to the server, that's really bad in terms of security because, yeah, it'll work for the majority of people, But if somebody with malicious intent, or really anybody from the club with like just a basic idea of how to use the Chrome developer tools, can go in there and find your function for the validation check and literally just change it to return true or return input is valid. And then they can hit the submit button, and then whatever input they sent will get sent back to the server because they just passed the validation check, because it's all client side. So you can change all of those things. So this just really hammers home the point that it's really important to always have server side validation as well. It's cool if you have client side, because again, for the majority of people, that client side validation will work and it will take some processing load off of your server. But again, for those more advanced people or malicious users, you need that server side validation so they don't do malicious things. Now, the biggest area of security whenever it comes to JavaScript, and the most common thing you'll hear about, is called cross-site scripting. Now, the name has always confused me at first, so don't get too hung up on the fact that it says cross-site. That can confuse people. And cross-site scripting is a huge research area that is always ongoing in the community right now. So don't worry about it if it seems really complicated. We're just going to go over the basics right now. And there's 3 different types generally that you'll hear about. The first is stored. So imagine that you have a user creation field, like you're logging into a new account. You're making a new account for this web application, and you set your username to some JavaScript, right? So you actually write in JavaScript code as your username, click create user, and your user is successfully created. And then you go to your profile page. Well, whenever your username's rendered, if the application doesn't do any sanitization or anything on your username, whenever that web page is rendered by your browser, it's going to execute that JavaScript in your username. So that means anytime anyone else goes to my profile page, that JavaScript will be executed. I believe this was the way that the MySpace worm, I think it was called the Sammy worm. Please don't quote me on that. I'm not 100% sure if that's the name, but I believe that's
I think so, yeah.
Yeah, that's kind of how it was done, was via stored cross-site scripting. So anytime anybody visited his page, I believe it would make them friend him, and then it would replicate the worm onto their page. So then anyone who visited their page would then get the same thing, and so on and so forth. So that's kind of what stored is. It's the code is stored on the web server, usually in a database, and then anytime that page that loads that asset is requested, it gets executed. The next most common is reflected cross-site scripting. This one is a little more confusing if you're not familiar with web stuff. This is basically whenever the JavaScript or the cross-site scripting is available through the request parameters. The most common example and the easiest one to think about is, say you have a search bar. So like the search bar on Amazon or Facebook or something like that. Whenever you type in a search query, generally those will show up in the parameters in the URL. So they're using get sometimes, the get parameters to do that. If you make a link, like craft a link, and this search bar is susceptible to cross-site scripting, say you embed some JavaScript into that search query that you type in, and then you send the link off to your friend or someone via email, and they click that link, the JavaScript will be executed because it's part of those parameters. So then you now have reflected cross-site scripting. And then the third type, it's not listed on the slides here. It is considered a third type. It's called DOM-based cross-site scripting. The DOM, just think of it as the HTML page. That's how you reference the HTML objects and stuff in JavaScript, is through the DOM. Whole other thing. We're not even going to go near that. I just wanted to mention DOM-based cross-site scripting. It's also called self cross-site scripting. And as the name kind of implies, it's really just against yourself. So it's a lot harder for DOM-based or self-based to actually get a security impact. But it is just something to be aware of in case you do hear that term. So again, since JavaScript is running in your browser, if you get cross-site scripting, you now have full control. You can run any JavaScript code. Granted, if there's no protections, we're not going into those. But if there's no protections, you can do things like steal their cookies and all that stuff. So JavaScript can definitely make your site more reactive. But it's definitely gives you a huge security risk if you don't have developers who exactly understand what's happening with it.
Real quick, I realize we're starting to get a little low on time, which is a bit of a yikes. But we'll touch on the developer console. All browsers have one. A lot of people like the Chrome one. I think the Firefox one is just fine, but pick one, use it. They have the developer console has lots of helpful features to help you analyze what's in a page. You can look at the whole source code of the page, like the HTML and CSS and JavaScript as it gets updated live, which often the HTML and CSS will be updated by JavaScript in a lot of pages these days. You can debug JavaScript as it runs or run your own JavaScript. And you can also look at all the various requests that are made by the page and just a ton of other stuff. Developer consoles are packed full of features, and they're really helpful both for web developers just trying to get their page to work and security folks trying to make pages break. So check out a developer console, play around with it, see what you can find.
Cool. So real quick, let's just go over some like random web stuff that didn't really fit in any of those slides. Super important thing to keep in mind for just security, web, and just CTFs in general is the robots.txt file. So most websites will have this file just right at their root directory. So you can go google.com/robots.txt. No idea if there's actually a file right there, but that would be the format of where it is. And this file is basically for all the web crawlers that are constantly yeeting out over the internet. And this file is going to define directories and files that they want to be indexed by the crawlers, and then also resources and files that they do not want to be indexed. Now, most crawlers will respect this file, but again, like you don't have to. There's no one, like there's no robots.txt police that's going to come like knock down your door if you don't follow this. But this file is super useful for like recon and whatnot because it'll kind of reveal directories that may not be linked on the original site, so it can give you some kind of like insider info, if you will. And again, we went over this earlier. HTTPS is literally just HTTP wrapped in TLS, runs on port 443. Normal HTTP runs on 80. Again, you can move those to whatever service port you want. Those are just the standard ones.
All right, so now that we've talked about what the web is and how it works, we're going to talk about 5 exploits and their mitigations, and then we'll be done. So we're almost to the end here. Just hang on with us. The first one we're going to talk about is cross-site request forgery. Ooh, it's a mouthful. Or CSRF, or CSRF, as it's sometimes pronounced. So with CSRF, what it generally looks like is that a user's already authenticated to one site, like say, for example, their bank account or their bank website. And then when they go to a different site, they're tricked to make a request back to the original site. So that's where the cross-site in cross-site request forgery comes from. You're making requests from across 2 different websites from one to another. And the request forgery comes from this other malicious site is forging a request that you didn't mean to send, but it's sending it on your behalf to do something that you probably didn't want to do. So we have this example here. Web page X is some totally normal website that has this endpoint that just allows you to change a password. And web page Y has a malicious image tag in its HTML, and it's got this image source, the URL that you download to actually get the image. It's got the image source set to this change password endpoint to change the password to lolhacked. Great security on web page X, but we'll just move on. So let's say Bob, our hapless individual, he's going to site X, maybe do a little bit of banking or whatever, logs in and receives his cookie. So now he's logged in. Then Bob's going to go to site Y. Maybe somebody sent in an email. He's going to click on this link. He's like, oh, wow, what's site Y? And then once the website on web page Y loads, his browser will automatically load this malicious image with this URL. And to download that image, that's what the browser thinks it's doing, it'll make that request over to site X. And since Bob is authenticated, it'll the browser will send Bob's cookies, and it'll send that change password request. And from the server side, it'll look pretty legit. And it'll make that new password, or that lol hacked password change. And then Bob's password on website X would be hashtag hacked. So that's a basic example of CSRF. Now, how do we mitigate CSRF? Because that seems pretty bad. Well, fortunately, there's kind of a lot of things that need to work for CSRF to work. First, you got to target a site that doesn't check the refer header in your request. Refer it if you think it's misspelled there in the slide, because refer, I think it's spelled with 2 R's or something. It is misspelled, but that's on purpose because the refer header, the standard, it's misspelled. So when you look at a header, it'll have refer misspelled. That's just how the world is. A little bit of interesting lore for you about the web. So the refer header in a client usually says where, like what website they were referred from to make that request. So if you're making a cross-site request, you'll set the refer to whatever site referred you. So usually sites should check that to make sure it's coming from the right place. So that's the first thing. Second thing is the attacker must be able to grab some URL that has some kind of side effect, like transferring money or changing a password, and they have to be able to actually make that request. Okay, so that's another thing. Usually, like password changes are a little bit more complicated than just saying post new password or get new password or something like that. Third thing, the attacker has to figure out all the right values for all the form inputs for that endpoint. Then they have to set that up on their malicious site, and they must have the victim who's already logged into the original site visit their malicious site. And the same origin policy needs to be ignored, which that's more advanced stuff that we're not going to talk about. But safe to say that there's a lot of things that need to work for CSRF to work. A really common way of presenting CSRF is with CSRF tokens. And this is server just generates a random token for each request and places it somewhere within the web page in some. I mean, it doesn't have to be hidden, but it's someplace that you might not expect it to be. That wouldn't automatically get sent. So say, for example, if you have a form, maybe the CSRF token is hidden somewhere in the form. And so what these CSRF tokens are good for is, say if you have a form submission to change your password, maybe you have a hidden form input that includes a CSRF token that would automatically get included with the form. And on the server side, you can check to make sure, okay, does this request have a valid CSRF token that I have already created? And so then an attacker can't spoof that form request because it doesn't have, the attacker doesn't necessarily have a CSRF token generated for that user. So CSRF tokens, look more into those. It's a little bit more complicated than what I just described, but that's the basics of preventing cross-site request forgery.
So we got cross-site request forgery. We got cross-site scripting. Instead of going cross-site, let's just go server-side request forgery. This is SSRF. I've never heard it called SRF before, but I guess you could call it that if you really wanted to. So the difference between this one and CSRF is this time we're actually going to trick the web server into making a request for us. So this is going to occur whenever you have basically like full or partial control of the requests being made. So the example I like to give for this, and it's going to be different from the one presented on this slide because I think it's slightly easier to understand. Say you go to a web page and you have your profile picture. Generally, that profile picture is going to be stored somewhere, and the web server, whenever you request that page, is going to send a request out to load that image, right? You're going to have to go out and download that image along with the website, like the web page itself. So what happens if you were allowed to set your profile picture to a URL? Similar to what Newman just talked about with the profile picture example he gave. What happens if you set that URL to the AWS metadata address as your profile picture? And then if you're allowed to do that and you load the page, very likely the web server will see that and then send out the request to go download that information. And if the web server allows that stuff to happen, it will send the request, and since it's coming from that server, it will get the information and return it to you. Now, the image is going to be dependent on whether or not the actual backend will fetch it for you or the client side, so it's not as consistent. However, that can work. The better example that it will be way more consistent is the one presented in the slides here, where if you have Apache and it has certain modules enabled, you can actually craft a URL to leverage the module that's enabled. In this case, it's mod status, and you can actually get local host server status information from the machine that's actually running it. So server-side request forgery is a little more complicated. However, it is extremely powerful and dangerous. If you achieve server-side request forgery, you can actually use it as a port scanning method to actually port scan the internal network. Right here. You can actually port scan the internal network. So if you're doing an external pen test and you get SSRF, that's super, super dangerous for the company. So mitigating that, it's going to be kind of similar to CSRF, but not exactly, because now you have to actually prevent your web server from doing things you don't want. So this is where firewalls and network policies are going to be really important. Like, your web server should never be sending traffic to your domain controller. Like, if it is, there's big problems and you need to re-architect your stuff and make that not a thing. But if it tries to, that should just be stopped by our firewall. And the common theme with all web defenses and preventions and whatnot is to sanitize your input and your output on both ends, from the client and the server. Input sanitization is the main theme, so you're going to see that with basically every exploit and mitigation. Also, you just want to disable URL schemes that you don't need. For example, if you don't know this, you can actually use your web browser as a file browser. So if you go in and you do file : whack whack, and then like /etsy/password if you're on Linux, there's a good chance it'll just pull up Etsy password in your browser. So think about, like, if you have, we'll go over this soon, but like if you're able to specify a different URL scheme to the web application, it might just accept it and then make that request for you and return a file for you. So then now you have arbitrary file read, which is not good. So just make sure you kind of disable everything, and also requiring authentication for internal APIs and services is also a good way to stop this from happening.
So next one is SQL injection. This is a fairly common one. These days, most websites, or most dynamic websites, are really just a front end for a database. They grab information from a database, make it look pretty, and show it to you. And SQL is a really common database format. Idea, whatever. It's a common database. And depending on how the backend is written, malicious users may or may not be able to modify the queries that the application makes to the database to get other information or get more information than they're authorized to look at. So one example, but slightly different, again, from the one on the slides, is, say if you're logging in to a website, you're passing it your username and your password. And you send those off to the server, and the server will hopefully run your password through some kind of hashing algorithm and then do a lookup in the database where it's going to select star from users where your username is equal to the username you passed and the password is equal to the hashed password. And it'll look for your username or your user record, and then hopefully it'll find you, and then you'll log in. Well, if the backend is just placing, doing a string format and dropping your input into a SQL command string, you could theoretically, well, not theoretically, you can pass special inputs as your username and password, like say not your username or password, gasp, as special SQL information to basically escape out of whatever SQL string that it's giving you and tell it to do something else. So this example here, where it's doing single quote or 1 = 1 semicolon hashtag, what that's doing is it's saying where user equals empty string or 1 equals 1. And 1 always equals 1. So it doesn't matter what the user equals. This will return all the users within the database. So you'll get all their information, the usernames, their passwords, any other metadata, at least in theory. And then the semicolon and hashtag at the end of that just comments out the rest of the SQL command, so that if there's some other stuff, it doesn't break it. SQL injection, there's a lot of different types to it. It can get pretty complicated. I think we'll go to the next slide now. But generally, to mitigate SQL injection, the answer is to two things: to sanitize your inputs, and do not use raw query strings. So first, with sanitizing your inputs, what does this mean? This means that anything that you're getting from if we're talking about server-side code, anything that you're getting from end users, which means any requests, you should never trust the content to be what you said it should be. So with a username and password, you shouldn't trust that they're actually passing you a username and password. You should sanitize those strings. So make sure that there's check those strings to make sure that any bad characters, like maybe a single quote, something that you shouldn't allow, make sure that those aren't in there. Make sure your inputs match the format that you expect, and there's no shenanigans going on. And that's not just for SQL injection, that's anything that you're receiving as a web server, or really any application. Never trust anything you receive from a user, because that input is how an attacker can try to break your application. So always, 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 if there's anything you get from this, it's to always sanitize your inputs. Another thing is never allow raw parameters in a raw query string. So if you're doing backend development, don't just have a string, like literally a string variable containing your query that you just drop parameters into. There's a few ways to do this. One way is called prepared statements, which a prepared statement is a pre-prepared query string that you have already registered with the database, kind of like a function. So you could, if you go back to the previous slide, that select star from users where user equals blah, you could create that on the database and say associate that with a name like authentication. And so you could say, here's my query string, here's where the parameters go, store this. You can go back to the negations. Thanks, Simon. So prepared statements are one way of doing that, because that separates your query string from the data, and oftentimes that can help prevent the data from escaping out of the query string, because the database knows that those are two separate things. Another way of doing it, which I actually recommend, is using some kind of abstraction layer or some kind of library. Instead of just making a connection directly to the database and sending string queries, most databases provide or have some kind of library in the language that you want to use. If you're in Python and you're doing SQL, SQL Alchemy is a good choice. If you're using MongoDB, there's Mongo Engine and a bunch of libraries. Elasticsearch has database libraries for pretty much every language out there. But these libraries will abstract away the nitty-gritty of working with the database and present to you some kind of interface that's much more native and comfortable for working in whatever language that you're in. So for example, with SQL Alchemy and Python, interacting with the database is much more like writing normal Python code than it is writing SQL commands. So libraries like those can make mistakes from time to time, but using those is a much better way of interacting with databases. And I will say, from the attacker side, libraries are also a good idea. So if you ever encounter some kind of challenge that you think might have, like say in a CTF, that you think might have SQL injection, a very common tool is called SQL map. It's basically the god tier SQL injection tool. It'll do if there's SQL injection possible, it'll handle it for you somehow. Sometimes when you're first learning, doing SQL injection manually can be a good learning tool, but eventually you're just going to use SQL Map to do it for you because it can do a lot more. It can try a lot more things a lot faster than you will be able to. So SQL Map.
Yeah, SQL Map's great. We're almost done, guys. I promise. We got this one and I think one more. But local file inclusion is another exploit, and this one's actually probably one of my favorites to exploit just because it's really fun and pretty interesting, the things you can do with it. So local file inclusion is just basically whenever you can get the web server to serve you a file that it didn't intend. So it's kind of like SSRF, but it's not making another web request, right? So it's just fetching a file or something like that. So for example, some websites will have like some code to preview a file. Say you're like hosting your resume on that server or something like that. And whenever you go to your page to view your resume, you see a link like here where it says vulnerable host / preview PHP file equals Simon resume HTML or Simon resume PDF or something like that. That's all fine and dandy. But what happens if we change that Simon resume PDF name to .. like etc. and then Etsy password? How is the web server going to handle that? Well, if it's vulnerable to LFI, what the web server is going to do is it's going to just follow that path and be like, oh, I need to fetch Etsy password right away. And it's going to go run off, fetch Etsy password and just return that and regurgitate Etsy password for you instead of the PDF or the resume or whatever page you originally wanted it to load. So this is super useful because you can use it to actually chain and then get RCE with it. There's a ton of phenomenal blog posts about how to chain LFI with other things to get RCE. But at the end of the day, it all revolves around somehow getting PHP code or some other like backend code into the web server and then requesting a file. And then since you request it and the web server processes it, it'll process the PHP first and return it. And then you can use that to get remote code execution on the web server. So LFI is a phenomenal vulnerability if you find it, and it's super fun to play around with because you can actually just go around and start reading arbitrary files. So it's definitely something to watch out for. Now, mitigation, again, sanitize your freaking inputs. We'll say it a lot and I'll say it again. Also restrict what your web server can read. Literally just keep everything, all the resources that you want in www data, and don't let the web server read anywhere else from that. Also, don't run your web server as root. Might be kind of self-explanatory for us, but if you go work at a company and somebody's like, yeah, let's run the web server as root because we want to provide this functionality that needs root access, you need to stand up and say, no, bad idea. Never do that. Because that means if an attacker gets LFI or anything, any file they request will be requested with root permissions, which is just bad, right? And also sanitize the inputs. So just don't let the user specify arbitrary files. Just build in the API endpoints you want the user to be able to hit and don't let them do anything other than that. Really just lock down your application. Seems straightforward to defend against, but as with anything, once you start developing a massive application, it becomes a behemoth of code and like things get missed and things get lost. So just watch out for LFI.
So last one we're going to talk about is command injection. This is similar to SQL injection in that you're providing input that just kind of gets concatenated with strings. So some endpoints might take some kind of input that it would use as part of a command. So for example, similar to the LFI example we had before, we have a resume endpoint. So maybe we're trying to get Simon resume.txt. Well, maybe the way this endpoint grabs the content of that is it just makes a system call to run cat and then the file name that you asked it for. Simple way of doing it if you just want to get it working, but it is bad to do because, well, if we wanted to, we could pass a semicolon and to terminate that command and then run our own commands. And now we can use it like a shell. So in this example, instead of sending Simon resume.txt, we're just going to send B. It's a random character. It doesn't really matter. add a semicolon to end the command, and then run ls. And then the thing that'll be returned instead of Simon's resume or B, whatever that is it'll return the content of ls. So we'll see all the files in whatever directory that it's running. And you can, use your imagination, run lots of other different types of commands with this sort of thing. So the mitigation for this is, again, sanitize your inputs. I hope you're noticing a theme. Input sanitization is really important. There's lots of different types of injection, not just SQL injection or command injection. Basically anything that you're interacting with that requires strings, like LDAP or something, you can do some kind of injection. So there's tons of different types that you could look into. But the way to prevent command injection is basically it's very similar to SQL injection. Just don't run raw shell commands from your code. If at all possible, which it usually is, try to do whatever you're trying to do with native like code function calls without trying to shell out into an exec or a system like a shell call. So with Python, for example, this resume thing, we could use with open as f and then f.read instead of trying to run the cat command. And that'll actually be more efficient. So not only will your code be more secure, it'll run better too. So it's a win-win. Also, again, don't run your web server as root, because if somebody gets command injection on your server and your server is running as root, now they have a root shell on your web server, and that's not good at all. But that's command injection. Pretty similar to SQLi, but a little bit different.
All right, guys. This side is just kind of like little tips and tricks that you can kind of peruse over, more things to like Google about. Basically, the web's really freaking complicated. As you've probably seen through the course of this presentation, the theme is like, here's what the RFC says, but you can do different if you want to. And the do different if you want to is really where all of these security problems come from. Because again, in these big applications, developers might not be aware of it, and they'll just kind of do something to meet their deadline, and it might not be RFC compliant, and that's where the security problems come from. So, and again, input sanitization is the key. We'll say it with everything. This applies to every area of security. Also in web, recon is a huge thing, as well as automation. Just one real quick, like personal example of it. I found local file inclusion on a web application I was testing, and I was able to chain that to achieve RCE. So now I'm able to run shell commands. However, the way to do the LFI and then the way to do the RCE was pretty convoluted and a long process. So instead of like doing that process for every little command I wanted to run, I automated it. I made a Python script I would type in my bash command, and it would go through the whole LFI and RCE process and return me the output. So that way I could very quickly enumerate the system until I could figure out a way to actually get an interactive shell instead of doing this janky chaining thing. So once you find something in the web, automate it. It'll save you a lot more time in your testing and everything. And that goes for recon as well. Newman, I don't know if you have any personal tips or tricks with the web, but
not really. Just want to reiterate that a lot of the web, there are a lot of standards that define how protocols should work and how things should be parsed. And there are areas in those protocols where things are suggested instead of required. So there's some leeway in how things can behave in that way, but also some things that you'll find as you do more stuff with web, and if you take CSEC 380, is that web servers and some web servers and websites just straight up break RFCs and standards. And you're going to have to deal with that. You'll find when you're dealing with the web. People don't always follow standards, and whenever you're interacting with the web, your goal should always be to follow the standard as closely you can yourself, but accept a wide range of input from other people so things still work. And that's kind of how the web has been programmed. So if you see things that are weird, that are like, that doesn't really follow the standard. Like an API request that returns a 200 error when it's really a server error. That's why.
Yeah.
So just know you might see weird things on the web. That's just how it is.
Yep. And then lastly, guys, here's just some resources. I'll try and get the slides up as fast as possible at the end of this. Really quick, if you want to have some fun, go read the RFC for HTTP and then go send some like curl requests and stuff to RIT, just like the straight up rit.edu, and then count how many like infringements there are. And whenever I was going through the CSEC 380 class, it was pretty wild, like sending a request to RIT and looking at how long a response was from them. Not that anything was terribly bad. It was just pretty interesting and kind of comedic to look at. But if anybody's got any questions, I'm looking at the chat now. I think Newman's looking at it as well. We can field some questions. Sorry it took so long, but the web is extremely complicated, and we wanted to give you guys the best start to, exploring the web. It's a fun time.
Yeah. I just got the
thanks, John.
Twitch chat open. Oh, thank you, John.
John's the real MVP. Everybody in person, give John a round of applause for being president during a difficult time. How do you make a website? You just Python.
There's lots of ways. But yeah, if you have any other questions, Simon and I were in Discord and we're on Workplace.
Yeah,
so
definitely hit us up. Our handles are at the beat. Newman, did you include your handle on your slide?
I don't think so, but I'm Sean Newman on Workplace.
Yeah.
So
the spider that makes the web comes from the NSA.